Start on the structure project.
So you were saying,
I'm not traveling, and
Yeah, I'm
you
doing
know,
that. And then I gotta do this project, and then I gotta do Dynamics project. It's just projects.
oh,
I
that.
just
Yeah.
got my EE valuing the E.
yeah, we're in the same section.
I always ask you that, and
I always forget
it's
to.
because I'm sitting anywhere. You know what? Yeah.
We sit on the other side of the room,
Yeah.
and behind me, and I'm like over there. In the
So
corner.
during the Tuesday section, I have my laptop before we get off of break. That lecture and last week and before Thanksgiving break, and now I have to go to another lab after. Like the Thursday people.
I have labs right up until the end for
So you know,
I don't have solid.
I have Dr. Oliver.
I don't have Dr. I have Dr. McNeil. I like him.
I really like Dr. Oliver. We have 2 labs left, which is 13 and 14. 14 is like an optional lab that isn't the material for that lab isn't covered in the course. And that is like, hey, if you're interested, you can come. But Dr. Oliver says no one ever shows up for that, so we just use it. The material that we cover isn't taught in lecture, so it's like, you know nothing going into it.
And it's the end of the semester.
Yeah, and no one's going to want to show up. So it needs to be optional. No one showed up, so we just canceled it.
All right, so 15 is on right there. How are you doing? Can you hear me?
So that makes sense.
Say something. Hello? Do you have audio? I assume so. Okay.
Yeah, so like the last 14. So
I think he's on. I think the.
He's on the cross country.
Yeah, cross country. Yeah. So I assume he is watching. Right? Can you react to something? Sum up or raise hand? Or... all right. So let's take in-class attendance. Don't worry about it. Okay. Yeah, don't worry.
Peter just sort of
I predicted my grade.
Look at there's context to this, I
As
promise.
soon as I walked out, I
It's
predicted my
exactly
grade like, okay, I'm gonna get this grade and I'm gonna lose my points because of this. And I get my grade last night, I'm like, I got the exact grade I thought, and I missed points exactly where I thought I missed them.
And who else?
And the mistake I made was like,
Everybody's here? Okay.
actually ruined it.
All right, so let's begin today. Oh, we need to switch to this. Okay, sorry. Let's begin with updates. Midterm exam 2 is over. And then everybody did great. I have no problem. Class average, I don't know. I don't even compute. If you're happy, you're happy. Like I said, it's not exam, okay? If you're doing homework, it's like cut and paste of homework. It's not exam. If you screwed up, that means you didn't do your homework. Period. It's not my problem, okay? Anyways, everybody did great. If you didn't do great, I think you know it because I sent you email. Okay. So if you didn't get any email from me, you're fine. So that's just to finish up the semester. We have how many more exams? One more exam, final exam. Do you know when?
No.
No.
Is it on
You
Monday?
cannot even think about it. Yeah, let's talk about that later. After the Thanksgiving. After the Thanksgiving, let's talk about final exam. Okay, so
Okay.
not now.
Sure. Sure.
It's just to
That's
keep
fine.
avoiding facing your reality, okay? That's fine. So just the updates, yeah. Yeah.
Specialize in it.
Oops, something wrong. I have to plug this one into the bracket. I don't know why. Outside the bracket, but I fixed it. So.
Interesting.
Yeah, this is software bug. Probably.
What's
This is a software C-Monkey, which is very crappy WYSIWYG HTML editor, which is freebie. Terribly crappy. Anyway, so It's not my fault. I think it's software's fault, but I'll fix it. So homework of Unit B3 is due Friday this week. Okay. Before noon, don't forget. Okay. You can do it, no problem. And then project 2A is due Monday, beginning of the Thanksgiving week. Okay, so if you want to enjoy the entire week, please do it early. Okay, you can continue working remotely with your teammates, however, but okay. Any question here? And then next week, Monday's class, all remote online, right? You don't show up here. I'm going to teach online, everybody online day. I'm going to teach from my office. And then Wednesday, Friday next week will be, of course, Thanksgiving. You don't show up. Okay. Go ahead.
Out of curiosity, why is this coming Monday online?
Because I know some of you may be already gone for
Oh.
Thanksgiving, which is I wouldn't say okay, but it's a fact.
Okay.
And then those people still can join in,
Got it.
pretending like, hey, I'm not taking extended vacation by myself. No. Go ahead.
For project 2A, would you be willing to share with us your code like you did for project 1?
I don't know. Negotiable. Publicly, I hesitated to, but you can try negotiating, sending text, and
Okay.
yeah, it depends.
No.
I can't guarantee yes answers for everybody. It depends on what you've been doing in this class and my impression kind of stuff. Scary, isn't it? But you can try.
Okay.
And then, yeah. Okay. Any other question? But it's, my code is by script. I don't think you can use it as is for your project anyways. But you can sort of understand what I did, sort of. Any other question? Okay. So today we are going to start Unit V4, application of potential flow analysis based entirely on Unit V3. So we spent sometimes, Unit V1 covers some math basics. Unit V2 started to use the mathematics to represent flow field, starting from streamline, and also viscosity included vorticity, irrotational flows, simplifications of it. And then what else did we do? We derived the process equation. Obviously, that actually showed up on your exam. And then the process equation, we started to solve it by method of superpositions of elementary solutions of the process equation, uniform flow source and sink, doublet, vortex. Am I missing something? I don't know. We are going to combine those things to construct the flow field. And then by the end of Unit B3, we talked about superposition of uniform flow and doublet opposing against it, trying to simulate the flow of a circular cylinder without spin. No lifting flow. That is the project 2A. Now we are going to talk about, okay, we want to actually start simulating the lift of a flow of a circular cylinder, lifting flow over a cylinder. Very simple idea is, obviously, you want to add the vortex with a magnitude gamma. By the way, what is gamma?
Circulation.
Circulation. What is circulation?
Yes.
Okay. What is the circulation in aerodynamic theory?
It's a mathematical.
Mathematical concept, yes. And then what does that mean in physical sense?
If you have like you can calculate the lift.
You can calculate the lift once you are given circulation of the flow field. Okay, here's the idea. Okay. The reason why we are going to do this practice, I give you actually 2 projects to work on. Okay, it's quite important to establish the baseline idea of how aerodynamic theory of circulation can actually compute the lift. You can apply that base idea, apply to the flow over the cross section of a wing, airfoil. Okay, so don't miss that kind of thing. Okay, so you have to consciously thinking about what is the meaning of doing this. Can we actually apply to do something when you become senior student and try to analyze the airplane's aerodynamics? Can we use this idea? Yes. So this is the idea. Basically, employed as a theory of aerodynamics, circulation theory. And then theory. This theory is based on circulation theory, okay? Circulation. Theory of circulation of aerodynamics. This is essentially German theory of Prandtl. Prandtl's theory of aerodynamics based on circulation. And then software, XFLR5, this is based on X-Foil. X-Foil is a software, original software developed by a professor at MIT, Professor Mark Guerrera. He developed this X-Foil. This is essentially panel method scheme. And then this software, X-Foil 5, is actually batch processing of X-Foil. In other words, you're going to run series of X-Foil inside of it so that you can use the data, you can build the database, and then you can design using the database. That's the X-Foil 5. So this is going to be introduced in project phase 3, A and B. Very, very fundamental introduction part of it. And then there are a few students already working on some advanced X-Foil 5 project. Please raise your hand if you're doing that. So those people are actually already working, actually specially tasked to use X-Foil 5 to do some meaningful airframe design and analysis. They are going to bring their findings, discoveries, and share it in the class toward the end of the semester. So please expect really high, expect super high something. Those 3 people is going to bring into this class. Be ready to ask a huge amount of questions and make sure it cooks very nicely.
Okay.
Okay, good. Sorry about that. But yeah, I guess there are lots of potential. You can use this software to analyze and design and analyze based off of the analysis. You can modify your design of airplane. That is something new. In other words, when I taught senior design project, when I came here 2003, aerodynamics is pretty much hand calculation. So someone's experiments were, someone's like a 20 years of accumulated experiences is huge. Airplane design is based on the paper. Okay, and then we design this way because I know this is going to work. Why? Well, because I have experience of 25 years. That was pretty much the aerodynamic design. Nowadays, you can actually use this software, okay, analyze based on this theory. So understanding the theory is essentially everything of aerodynamics. Lots of people actually trying to pass this class, not willing to understand it. That is essentially a huge amount of waste of time. Okay, then you're going to realize it when you become senior student. Okay, so please don't do that. It's a priceless thing. How many people actually cover this kind of thing in this country? This is one of those few places you can get that. Okay, so the reason why we're doing this is the circulation. Circulation is the key. Now, circulation actually gives you a lift, right? Have you ever seen this? What's that? This is the Kuta-Joukowski theorem, the most important theorem of aerodynamics. Okay. So once you know the circulation of the flow field, you can actually compute the lift out of it. In other words, in your project 2A, because there's no circulation in the flow field, flow over the circular cylinder is completely symmetric up and down. There's no way you can generate the lift. However, once you add the circulation by adding the vortex, you are going to simulate the flow over circular cylinder with spinning. You can determine how fast you want to spin the circular cylinder. In other words, you can freely choose how much circulation you want to add. You have a complete freedom of choice of doing that. And depending on the amount of circulation you add, you're going to control the amount of lift of this flow field. That's awesome, wonderful. Now, let's just fast forward a little bit. Can we apply that same idea for the flow around an airfoil? Yes, we can. It's the same idea, but it's slightly different. Okay. Now, when you design a cross section of a wing called airfoil, you're going to design the shape, right? You're not going to design the amount of saturation. It's opposite. So you're going to shape your surface. Then under the condition of certain angle of attack, okay, placed in the uniform flow, it is going to actually generate the circulation, right? So you are not controlling circulation. You are controlling the shape and then angle of attack, flight conditions, okay? Based off of that given shape and angle of attack, Reynolds number, possibly, you're going to compute circulation. That circulation actually determines the lift. Slightly different. However, basic mathematical mechanism is exactly the same. Okay. So the big difference between your project 2B and then this one is, project 2B, you're going to determine circulation. That is going to be the lift. Shape is circulation, of course. Shape is fixed. Okay, now in this case, you're going to change the shape. Based on the change in shape and angle of attack, you're going to compute the circulation. Okay, essentially the same thing. So be careful about that. Question, anyone, please? So stay focused on what you're doing. Again, the same exact mathematical concept is applied. So let's move on. So mathematically speaking, the great thing about this practice is everything is mathematical because we are solving the process equation. Okay. So we do know the equation for that stream function. Right? You're going to superimpose uniform flow and double it opposing against. You've got stream function of this flow field, and then you're going to just add one more thing. Then this is the flow field. Okay. So the equation now becomes three things superimposed. Okay. So this thing is a non-lifting flow over a circular cylinder, your project 2A, and then you're going to add a vortex of strength gamma, which is circulation. Okay. Then you're going to go through the exact same mathematical process starting from psi. Take a partial derivative. This is again polar coordinate. You're going to get the velocity field. Sure. What's next? After you get the velocity field, what's next?
You find the stream.
Well, you can draw a stream line, yes. What's next?
The side.
Stagnation point.
Stagnation point.
Yeah, stagnation.
Stagnation point is next. So before stagnation point, of course, like Robert said, you can draw a stream line. Yeah, sure. Right? And then you're going to determine stagnation point by setting velocity equal to 0. Right? As usual. And then you've got, set B, R, B theta both equal to 0, solving R and theta for the stagnation point. Okay? So let's just take a close look at what kind of stagnation point we can expect. It all depends on the amount of circulation you have. Okay. If the circulation is 0, what kind of stagnation point did you have? Non-lifting flow. Remember that? Project 2A. Circulation 0 case. Where is the stagnation point?
Right on its front.
Here, leading edge. Here, trailing edge, right? So you've got two stagnation points if the circulation is 0. So this is the flow field you're trying to construct and complete project 2A. Is that correct? So this is the case circulation 0. So suppose if you start adding circulation, what happens is, okay, two different kind of cases. First case, here. For lower rate of spin, circulation is less than the threshold. Stagnation point remains on the surface. Okay? So suppose starting from here, you are going to start adding circulation. Those two stagnation points starts moving downward, starts moving. Okay? Okay, stagnation point is modified, still on the surface, however, not leading edge and trailing edge anymore. Okay? And then you continue to increase. So that means those 2 points start moving toward this location. This location. Theta equal to negative half pi. Okay? Then if you spin more, what happens? This is going to depart from the surface, creating stagnation point around here. That is the condition of that. So 3 different cases you can expect, okay? Stagnation, yeah, go ahead.
So your stagnation point can only separate from your cylinder as long as it's along the axis?
That's right.
Okay.
That's right. So when you start adding the circulation gamma, first thing you notice was stagnation point still remains on the surface. However, it is going to start moving toward the theta equal to negative half pi point. And then you are going to create a single stagnation point right here. And then if you spin more, starting from here, stagnation point departs from the surface. And more and more and more. So those are the 3 different mathematical operations you can do, those kind of things. So if the circulation is less than 4 pi b infinity r, well, how come it's 4 pi b infinity r? You can find out by doing your homework, of course. I purposely does not go through any math detail, because everything is homework. So it's important to do your homework first, okay? So by doing your homework, you're going to find out this is the case that you still have the 2 stagnation points still on the surface, okay? So the stagnation point is little r is equal to capital R, which is on the surface of the circular cylinder. 2 locations, theta-wise, this is theta 1, theta 2, 2 stagnation points. Mathematically, you can find those as one of those homework assignments, okay? And then if the circulation is exactly equal to 4 pi b infinity r, those 2 stagnation points meet up here still on the surface, but the location is theta is minus half pi. Okay? Single stagnation point. And if you go more than that, stagnation point departs from the surface. Theta is still minus half pi. But the little r is more than capital R. It's no longer on the surface. So again, this is the stagnation stream, right? You have to find out the equation of this particular stagnation streamline and then plot in MATLAB. Yes, mathematically you have to find it. That's one of those homework assignments. Don't skip those homework assignments before you do your project. Go ahead.
Where's little r again?
What are you talking about?
You said little r is bigger than
Little r is a coordinate of a polar.
Oh.
R and theta coordinate we are talking here.
Oh.
Okay? Again, capital R is radius.
Yeah.
Yes.
Everything is polar coordinate, like that.
Yeah.
Of course, you can, using MATLAB, you can coordinate transform from polar to Cartesian anytime, x, y. And Cartesian to polar, R and theta, anytime. Okay. Question?
Are there cases where your stagnation point detaches from the surface of like your wing, like due to like a lot of circulation?
Due to a lot of circulation.
Yeah.
You are talking about flow over wing.
Like a wing. Yeah.
Let's not try to leap forward too fast, but the answer is yeah, but your software cannot handle that. Okay, too bad. X55 cannot handle that, period. Because that is essentially Panel method. If the flow separates from the surface, Panel method basically says, error, we cannot converge. Error, we cannot converge. Have you ever seen that? Yeah, it happens all the time, right?
Yeah.
That's when the flow separates from the surface. Panel method actually combines this plus surface boundary layer simulations. Okay, we're going to talk about that step by step. Okay, don't move too fast because everybody else is left behind. I don't want to do that. Okay, any other question? So this is something you have to do in project 2B. Okay. So I purposely did not show any much detail, but those are the summary of what you need to be doing. You have to find out, okay, lots of things, mathematically speaking. First of all, starting with what is the psi, which is the stream function, to construct those 3. Essentially, equations are all the same. The condition is only the value of circulation. If the value of circulation is this value, you are going to have a single stagnation point If you have lower than that, you have two stagnation point. If you have higher than that, it's going to be single stagnation, actually two stagnation points.
One of them doesn't matter.
This one doesn't matter. This is called trivial solution. Stagnation point is formed up inside of the body. Mathematically correct, but physically it doesn't make any sense. You're not going to choose that as your solution. It's called trivial solution. Okay. This is the only physically correct solution. Let's be careful about that. You have to do all of those things in your homework assignment. First of all, please do that. Don't skip those. Okay. Any question?
You're talking about the B3 homework assignment, right?
Oh yeah, which is due Friday.
Yeah.
Sure. Well, no. That's B4.
Okay. So
B-
B4 is the same.
This is B4. Okay. So we are not even talking about when is the due of homework, or solution of homework B4. Project of a 2B, or homework of B4. We are not even talking about when is the due, but you have to do the homework before you do project 2B. That's what I'm saying. Okay. All right. So let's just take a look at example, class example problem B41. Consider the lifting flow over a circular cylinder. Based on the potential flow analysis, derive the relationship between lift coefficient and the circulation. Didn't we do this? Do you remember?
We did this without a GAN.
That's right. So now we are going to actually plug in CP, which is not a uniform. It's not anymore 1 minus 4 sine squared theta. Okay. So let's just take a look at it. Okay. So this is probably very important practice here for your project and also your homework. Okay. But before we start moving on, have you ever seen this program in Unit B3? I want to know, everybody understand. I think we did this in Unit B3. Which page we did that? Please. Yeah.
Is it going to be page 13?
Page 13 of Unit B3, is that right?
Oh, it's 12, but
It's
Page 12?
yeah, 12 and 13.
Okay. Huh? Did I do that? Oh, yeah, okay. I will probably have to show my master note. But, okay, let's take a look at Unit B3 note. Page 11. Okay. So we came up with the velocity field over the surface of the circular cylinder, R equal to capital R. This represents the surface of the circular cylinder. Over the surface of the circular cylinder, velocity component is only in theta direction, we know that. And then we just subtract into the CP equation to get CP equation. This is the flow over non-lifting circular cylinder surface pressure distribution, CP distribution. As you can see, this is sine function, completely symmetric. Upper and lower surface, there's no lift generated. That's what we found, okay? The rest is the process I think we covered. So if you plug in the CP into the integral equation from leading edge to trailing edge of the CP distribution of upper and lower surface, it's going to give you a lift coefficient, right? Right? Mm-hmm. Now, if you plug in CP here, it's going to be 0. Sure. Now, suppose if you superimpose circulation, it is going to alter the CP. CP is no longer this function, right? Okay, let's find out. Okay. I hope you're following it. Otherwise, you probably have no clue what I'm talking about. So anyways, we are going to pick up the velocity field equation to begin with. Velocity field is, okay, So again, starting point. Stream function psi is equal to b infinity r sine theta 1 minus capital R square over little r square. What is little r, by the way? Just coordinate. Because we're talking about r and theta. Okay. So remember, stay focused. This is the coordinate we're dealing with, r and theta, polar coordinate. Okay, so now you're adding gamma over 2 pi, natural log r over r. So this is a starting point. This is the stream function governing this lifting flow over circular cylinder. And then obviously in polar coordinate, velocity is BRER. That's B theta E theta, correct? And then we can determine BR in polar coordinate, 1 over R d psi d theta, in which, if you do that, this is going to be 1 minus r squared over little r squared, b infinity sine theta. B theta is negative d psi dr. Okay? This is minus 1 plus r squared over little r squared, b infinity sine theta minus gamma over 2 pi r. Now we found velocity field, right? And the next step is, okay, so what is the velocity field on the surface of the circular cylinder? Okay, that is basically doing this. Okay, so next is lit. Lit what? How do you represent velocity on the surface of the circular cylinder? Anybody?
Oh.
Yeah.
Little r equals big R.
Little r is equal to bigger r, so this means surface of the circular cylinder. Is that correct?
Yes.
Okay. Okay, so if you do such a thing, you can determine, okay, velocity field on the surface of the cylinder. So if you plug in little r equal to r for BR, what is it?
0.
BR is 0, that's right. BR is 0. Like I said, on the surface of the circular cylinder, obviously, you only have a velocity in tangential component only. Right? So B theta only. There's no BR on the surface of the circular cylinder. So what is B theta? B theta, you plug in little r equal to capital R here. So this is going to give you, yeah, that's right. Minus 2 comes up, yeah, that's right. Minus 2 B infinity sine theta minus gamma over 2 pi r. So gamma over 2 pi r is something added. That's right. Something added because you added circulation. Gamma term added. Go ahead.
That'd be big R.
Shouldn't it be big R? Yeah, under
Yeah.
circulation.
Sorry. Good point. This is capital R, so 2 pi r. Oh, okay, so velocity distribution. Okay, so let's just plug in Cp. Cp is equal to 1 minus, okay, b over b infinity squared. So clearly from here, velocity b magnitude is b theta anyways, right? Because there's no br important. So let's just plug in that. This is going to give you 1 minus 4 sine square theta plus 2 times gamma sine theta divided by pi capital R b infinity plus gamma over 2 pi R V infinity square close bracket. This is CP. Here we go. So CP actually have an additional term because of the circulation you added. This is the CP. Of course, those two terms are added because the circulation is non-zero. Suppose if you plug in circulation equal to 0, of course, you're going to represent CP equal to 1 minus 4 sine square theta, which is equal to essentially non-drifting flow, correct? Okay. So now, let's take a look at the handout. Okay. So which handout do you have to look at it? Well, handout of B4 to B4B, okay. Handout B4B. This is essentially the handout, exactly the same handout of B3B. The only difference is CP is different. Everything else is exactly the same step-by-step mathematical process, okay? So I hope you remember that. What we did was, okay, in unit B3, we did exact same thing. First of all, coordinate transform from here to here, streamline S coordinate to Cartesian X coordinate transformation, okay? Sorry, not this. Okay, sorry, from here to here. So this is the streamline S coordinate into Cartesian X coordinate transformation based on this. Okay. And then this is lift coefficient. Lift coefficient is essentially CP difference between upper and lower surface, integrating from leading edge to trailing edge. Essentially, conceptually, exactly the same as if you do the same thing in wind tunnel testing. Okay. If you are given pressure distribution of your cross section of a wing on upper surface, lower surface, CP upper, CP lower, what is the difference between them over the surface from leading edge to trailing edge? If you integrate it, it's going to be lift coefficient. You're going to do the same thing after you start taking wind tunnel class. This is the concept. Okay, make sure you understand the concept at least. Otherwise, Dr. Traub is going to probably snap it and then kick you out from the wind tunnel lab. I give him permission to do that. So that's the concept, okay? So after that, because this is a polar coordinate, you're going to again coordinate transform from Cartesian to polar, which is theta, okay? What is the coordinate transformation equation, which is coordinate transform? Oh, I'm skipping it. Well, I think, where is the coordinate? Let's take a look at handout.
What, like x equals r cos theta and y equals r sin theta?
That's right, something like that. I just wanted to show. This one. So this is coordinate transformation from Cartesian to polar, x equal to r cosine theta, dx is minus r sin theta dz. So you do the exact same math here. Coordinate transform from Cartesian to polar, and then CP is now, this is the CP. You just drive all the way in here. Okay? So now you are going to be given this horrible looking integration from 0 to 2 pi over the polar coordinate system. However, important thing is, this is important. Integral from 0 to 2 pi sine theta d theta is 0. What do you mean by that? That means this is 0. Okay. Integral from 0 to 2 pi sine cubic theta d theta is 0. Oh, I see. That means this is 0.
No, one to the left.
No.
One to the left.
One to the right, right? This is, oh yeah, okay, this is 0. Okay. So that means, ooh, this is 0. This is non-zero because sine square theta d theta. So this actually, the whole thing is pi comes up. This is what?
Well, sine of theta is.
Sine of, yeah, this is 0. Ooh, only one unknown, well, non-zero term is here. This is only non-zero term comes up. And then you know that the integral from 0 to 2 pi sine square theta d theta, this thing's pi. Right? Here it is. So this is the theoretical solution of lift coefficient of the flow over spinning circular cylinder or lifting flow over circular cylinder. CL is equal to whatever the circulation given divided by radius and the infinity. That's it. This simple equation is a theoretical solution to determine lift coefficient. Okay, you can use this equation to compare against what you do in project 2B. Okay.
Doctor, I have a question.
Go ahead.
What does the S and the X stand for in the quotes?
What is what?
Like the S, like what does the S stand for in the quotes?
S is the streamline coordinate. This S?
Yeah.
Yeah, I think so. Or the S in the orange.
This is A5. You can take a look at A5. This is the streamline coordinate. In other words, you remember in A5, we talked about this is a coordinate S, location A. This is upper surface S. If this is lower surface, this is SL. S is a coordinate over the surface of the contour, streamline coordinate system. Please take a look at unit A5, okay? And then if you still have questions, I can walk over with you, okay? All right. So I want to move on next page, okay? So the rest is handout. Please take a look at it because you have to do it anyways for your project. Next page, okay? So let's compare what we did against the real flow. The real flow is something called, okay, so this is Magnus effect. This is the real flow. Okay, so those two actually flow visualization. I believe this is the flow field, either smoke wind tunnel or maybe particle trace in the water tunnel. Either way, I don't know exactly. But this is the case that the roll rate of spin, as you can see, two stagnation points formed up here. Can you see that? So it looks like this is a stagnation point, this is a stagnation point, right? Flow is going around it, two stagnation points. Now, if you spin more, obviously, whoa, stagnation point starts forming up here. So the flow is coming in and wrapping around the surface and then depart like that. Okay, this is high rate spin. This is a low rate of spin. This is one stagnation point, another stagnation point. Flow is going around, flow away. Okay, this is Magnus effect. Because of that non-symmetric flow field, you are going to overall create lift. Okay, this is a two-dimensional flow, lift per unit depth. And then low pressure zone, high pressure zone, because the velocity is different. Okay, those two pressure zones are created. Let's just confirm once again using most important theorem of aerodynamics. What is it? Joukowsky, I cannot spell. Why? Joukowsky. Joukowsky theorem. Okay. Joukowsky theorem basically says lift per unit span can be computed by density of the free stream. This is the free stream velocity times circulation of the flow field, right? Okay. Let's call this equation 1. And also, let's remember, what is the definition of lift coefficient? Somebody please tell me.
It's going to be M.
Why M?
Yeah, it's going to be, sorry, L.
L prime over what?
C. Q infinity.
Q infinity.
C.
C. Yeah. So this is Q infinity, what's Q infinity?
Dynamic pressure.
Then of course 1/2 rho infinity B infinity squared multiplied by C. Okay, so from here you can say L prime is 1/2 rho infinity B infinity squared C. Let's call this equation 2. Okay, let's set equation 1 is equal to equation 2. That is rho infinity B infinity gamma Kuta-Joukowski theorem is equal to, go ahead.
Are you missing the coefficient of lift in equation?
Yeah, that's right. C times CL, right? This coefficient is missing, so yeah, good point. Yeah, that's right. So this is going to be 1/2 rho B infinity squared C times CL, lift coefficient. Now obviously, by looking at it, density cancels. One of the B infinity cancels. So also, let's note, what is the chord length? This is 2 times radius, isn't it? About 5 more minutes. So from here, what you can say is gamma is equal to 1/2 B infinity, chord is 2R times CL. 1/2 and 2 cancels. So what is CL?
Didn't we just solve for this?
Gamma over RB infinity. Oh my goodness. Did you see this equation somewhere?
Yeah.
That's right.
Neat.
Confirmed. Okay. Confirmed your handout. So suppose if the handout kind of problem shows up on final exam, you can of course handle that mathematically, and then you can confirm using Kuta-Joukowski. So one of the nightmare scenario is, okay, well, this is a final exam problem. Find out CL as a function of gamma and R. Do all the full mathematical details, and then confirm against Kuta-Joukowski. All of a sudden, your final exam is nightmare. Like I said, I can easily create that kind of environment in Elementor.
So there's just gonna be one problem.
Well, final exam is like, how many problems do you want to solve? 2 hours.
None, but you know. I'm not
How many
gonna-
hours?
2 hours? Well, you solved the 3 problems for 50 minutes. So technically speaking, let's say 7.
Yeah, let's see that.
Well, it's a final.
7 or
7.
5 if you make one of them longer.
Either way, negotiable.
No.
So please bring your opinion about final exam. I'll be happy to hear. Okay. Any question? So we stop here today, but as we come back on Friday, let's just start applying whatever we learned into the flow of a cross section of a wave. We are going to kind of step into more for the software, X-file and X-file 5. How does it work? Kind of thing. Okay. All right. That's it. Have a good day. See you guys back on Friday.
After talking
Friday.
Thank you.
Hour 4.
Okay.